All right, y'all. So in the first step here, the general idea is that we have our PLP cofactor represented here, and it's anchored into the active site through this shift base to the lysine side chain. So this lysine is part of the enzyme. So our cofactor is always starting off anchored into the active site, so it's always positioned correctly. And the general idea for step one is that an amino acid comes in and the nitrogen on the amino acid replaces the nitrogen on the side chain of lysine, so a new shift base is formed. Okay? And the way this happens is fairly straightforward. There's a lone pair on this nitrogen, okay? So in this case, our nucleophile is going to be the lone pair on that nitrogen. The electrophile in this case is going to be this carbon right here, okay? Because what we see is that the new bond that gets formed is between the nitrogen on the amino acid and the this carbon on our PLP cofactor, okay? So the first step is for there to be a nucleophilic attack of the nitrogen onto that carbon. Remember, a biochemist's dream, make a bond, break a bond. So we make a bond between the nitrogen and the carbon, and the bond we're going to break is the pi bond between the carbon and the lysine nitrogen. Okay, so we form this intermediate where the lysine, still having one proton, now has a lone pair. It has a single bond to our cofactor, right? So here's the rest of the cofactor. I won't draw the rest of it. And now this carbon also has a bond to this, right? So there's now a bond between the cofactor and our amino acid. So our amino acid is here where we have our CO2 minus and we have our R group. Okay, so at this point there is a covalent interaction between the cofactor PLP, the enzyme, the side chain lysine, and also the amino acid, which is the substrate. Okay? What we now need to do is, let me get a different color here. What we now need to do is to break this bond and end up with a double bond here. So we want to end up with a pi bond here. Okay? We also want to release the lysine with an NH2, and this hydrogen ends up, or this nitrogen ends up with just one proton. So the idea here is that the lone pair on this nitrogen will pick up a proton from somewhere. And just for simplicity's sake, I'm going to show it picking up a proton from the nitrogen on the amino acid. Now it could most certainly pick up a proton from a general acid in the active site or a water. But the idea is that we end up picking up a proton on this nitrogen, and this nitrogen ultimately loses a proton. Okay, and we made a bond between nitrogen and hydrogen. We now need to break this bond. So the electrons in this bond will end up moving over here, making the pi bond between the nitrogen and the carbon. And now finally we need to finish this by breaking the bond between this carbon and this nitrogen. So what we see here is in step one, the lone pair pick up a proton, creating our NH2. That also creates a temporary positive charge on the lysine nitrogen. The electrons in the bond between nitrogen and hydrogen end up moving over to create the pi bond between our cofactor carbon and the nitrogen on our amino acid. And finally, we release the lysine side chain by breaking the bond between our cofactor and the nitrogen. And we end up with a lysine with an NH2. We know it's probably NH3 because it'll pick up a proton. But the point is that we've released the lysine, we've broken that covalent bond, and we've ended up with a new shift base here between our cofactor and the amino acid that's our substrate. Okay, so that's the first step, and this is the first step in absolutely, whoops, what happened here? This is the first step in absolutely every single, I'm not sure what exactly happened. What's happening? Okay, so this is the first step in absolutely every single PLP mediated reaction. the shift base between the lysine side chain of the enzyme and our cofactor is replaced by the incoming amino acid. This is the same every single time. Okay? In our second step here, what we see is that, let me use a different color. What we see here is that we're shown a general base, and during this reaction, the general base gets protonated. Okay? The proton comes from the alpha carbon of our amino acid. So what we see here is that this proton ends up on our general base. We also note here that there's a different distribution of electrons in our PLP cofactor, right? So originally we have a single bond here, a double bond here, and this changes so that now the double bond is between the alpha carbon and the nitrogen. There's a single bond between the nitrogen and the cofactor. So during this deprotonation event, we basically are shifting the electrons to form a different resonance form, and ultimately the electrons in this bond right here are given to this nitrogen, because at the end we're going to see that this nitrogen has a lone pair. Okay, and this is one of the key ways that PLP works, right? We talked about how PLP is a really useful cofactor because one of the bonds on the alpha carbon is in the plane of the pi system. So it's really reactive because the electrons are drawn towards this positive charge. And that's exactly what we're seeing here. This CH bond is particularly reactive because the electrons are drawn down towards that electron sink. So let's show this happening. The lone pair on our general base picks up the proton, and the electrons just flow down, creating a different resonance form, and the electrons are ultimately given to the nitrogen on our PLP cofactor. We have now released this hydrogen, this proton, and we are left with a different form of our cofactor, right? Where our alpha carbon no longer has that bond with hydrogen. So it's now sp2 hybridized instead of sp3. Okay, in step 3, we're starting off with our sp2 hybridized carbon here. Okay, let me switch colors. So we start off with our sp2 hybridized carbon right here. Note that it remains sp2 hybridized. Okay, so what's happening in this step really has nothing to do with our alpha carbon or our carboxylic acid or our R group. If you note, what's happening boils down to this general acid in the active site becoming a base, so it gets deprotonated, and this proton is going to end up on this carbon of our cofactor. Okay? The other thing to note is that our resonance structure has changed. So we're starting off with a lone pair on this nitrogen, right? So there's a lone pair here. In the product, we have lost electrons on that nitrogen, and those electrons have shifted up through the pi system. So ultimately, these electrons right here are what end up making the bond between this carbon and this hydrogen. Okay? So let's show this. Once we recognize what happens, it's fairly simple to make it happen. The lone pair, we move electrons up through the pi system, and then when we break this pi bond, it then picks up that proton, creating a general base, and this carbon now has that hydrogen attached to it. This nitrogen ends up electron deficient, so it has the positive charge. Our electrons are distributed differently in our benzene ring, and this carbon ends up sp3. Okay? So that's step 3 in this transamination reaction. In step 4, we're told that the shift base is hydrolyzed by water or hydroxide. Okay? So we need to show water or the deprotonated form of water coming in. So in this case, hydroxide, right? We're explicitly told that hydroxide is going to be a reactant. So if you want to show water getting deprotonated, by all means do. But if you would like to just kind of ignore that step and recognize that there's general bases that can easily do this, then that's fine too. at the end of the day, what I need you to realize is that hydroxide is going to be our initial nucleophile. So in this first part, this hydroxide right here ends up bonded to our alpha carbon. So our alpha carbon goes from sp2, becomes sp3, and the new bond is with the oxygen from hydroxide. Okay? So you'll also note that this nitrogen starts off sp2 and ends sp3, right? There ends being a lone pair here. So the electrons in this bond simply are given to that nitrogen. Okay, so let's go ahead and show it happening. Okay, so choose a lone pair, it doesn't really matter. The idea is that it attacks at our alpha carbon, and simply the electrons are shifted down onto that nitrogen. There's now a lone pair on that nitrogen. Okay, in the next step, we have this general base present, and we note that that general base gets protonated. Okay, so what else is happening? The proton that ends up on our general base is coming from the hydroxide, right? So this alcohol functional group is what gives the proton. Okay, these electrons, we note, end up as a carbonyl between our alpha carbon and this oxygen. Okay, and we break this bond. Okay. Also note here that this nitrogen starts as an NH and we end up with an NH2. So even though it's not shown, we should kind of recognize that there's a general acid around somewhere that can donate a proton. So I'm just going to show that just as the proton sitting here. Okay, whoops. All right, so let's show this in a different color. So I'm going to go ahead and show it in blue here. Okay, so the general idea is that our general base is the nucleophile. It picks up that proton. These electrons move down to make our pi bond, the carbonyl, and then the electrons between this carbon and this nitrogen will flow over and pick up a proton from some general acid. Okay, you can show that general acid, you can make that general acid being a water, whatever you want. At the end of the day, we just show that it picks up a proton and we end up with an NH2. We also end up with an alpha keto acid. And remember, the production of that alpha keto acid is important. Through these 4 steps, what we have done is, let me move back here, right? We started with an amino acid. That's one of our first substrates, right? That's one of the substrates in this transamination reaction, an amino acid. And this amino acid gets converted to an alpha keto acid. So this is one of our products. And what I hope that you recognize is that this happens because we have removed the amine. And instead of the amino group, instead of this ammonium floating around in the cell, it's anchored and stored covalently on our cofactor. So we avoid the problem of this amine being able to freely be distributed out into the cytoplasm. So we don't have the problem of the mass production of ammonia because that nitrogen is stored right here on our PLP cofactor. Okay? The rest of this reaction is really just this process working in reverse, right? The first half, step 1, is converting the amino acid into an alpha keto acid. Step 2 is going to be bringing in another alpha keto acid and transferring this amine group from our cofactor and giving it to the alpha keto acid to create a new amino acid. Okay? And this really happens very straightforward in reverse. So we start off with our cofactor with the amino group here. We bring in a new alpha keto acid. Okay? And note here that step 5 is genuinely going to be the reverse of step 4. Step 4, we produced the cofactor with the amine group and we produced an alpha keto acid. We produced a general base with a proton. we're going to reverse this. So in this step, we ultimately want to be using this nitrogen as a nucleophile. We probably need to have some sort of a general base here to be able to do that. So I'll show this in red. The general base reaches over, picks up a proton. Those electrons are given to nitrogen. This lone pair then attacks here, and we will then pick up a proton from our general acid. Okay, this step is exactly the reverse of step 2 of the previous step. This then generates our general base. It reproduces it. We have our alpha carbon being sp3 hybridized attached to a hydroxyl group, and the alpha carbon is now attached to the nitrogen, which is anchored on our cofactor. Okay? In the next step, we want to release hydroxide. Okay? What we note here is that we create a double bond between our alpha carbon and the nitrogen, whereas we started off with a single bond. And we break the bond between the alpha carbon and our hydroxide. So this happens through a lone pair of nitrogen forming that double bond, allowing us to release hydroxide. So a product here is hydroxide. Okay, and this is important because hydroxide was a reactant in the previous step. So in the previous step, we use hydroxide. In this step, we produce hydroxide. So that's not part of the net reaction. We have now produced an intermediate where we have a new amino acid anchored onto our PLP cofactor. Okay, this step is the reverse of step 3 in the first part. Okay, let's look at what's happening. So in this case, nothing is really changing in our amino acid, right? Everything with the amino acid looks the same. So we can ignore the amino acid. So the chemistry happening here is happening in the cofactor. We start with a general base, we end with a general acid. And we start with the electrons distributed differently in our cofactor. We note here that there's a single bond, here there's a double bond, and the resonance in our cofactor is different. So that's really what's happening here. We have a CH that gets deprotonated. The electrons get pushed through our cofactor all the way down to our electron sink nitrogen, right? And again, we see how the chemistry of our cofactor becomes really important because it allows us to break a CH bond, just like we did way back in step 2. So the chemistry within our cofactor makes CH bonds labile when normally they are not. Okay, let's move on. In the second to last step. So in this case, we are changing the look of our cofactor. Oops. Oh no. So in this step, we are changing the look of our cofactor, right? So we see a different distribution of electrons in our cofactor. And we also recognize that we start off with a general acid, it gets deprotonated. We start off with an sp2 carbon, we end up with an sp3 carbon. So what we're going to do is take electrons from this nitrogen, push them through our cofactor all the way up to make the bond between this carbon and that hydrogen. Okay, so the electrons get pushed through all the way up, picking up that proton, deprotonating our general acid, giving us our sp3 hybridized carbon, the original look of our cofactor, and we have deprotonated our general acid. We're almost there. The last step is the reverse of the very first step. This is where the lysine comes in. It attacks the carbon of our cofactor. These electrons flow over to the nitrogen of our amino acid. That ultimately, recall, forms this intermediate. I won't draw the whole thing out, where we have the lysine attached to the cofactor also being attached to our amino acid. And now The second half of this reaction is the lone pair of our amino acid picks up a proton from that lysine nitrogen. We form the shift base between lysine and our cofactor, and we release the amino acid. Okay, so we've formed a new amino acid. We have regenerated the original form of our cofactor, the PLP anchored to the side chain of lysine within the active site through this shift base. Okay, so overall what's happening here is we start off with one amino acid, we bring it in, it reacts with the PLP cofactor. In that first half of the reaction, we produce an alpha keto acid by releasing ammonia. This ammonia is anchored onto our PLP cofactor, so it's not released. We then bring in another substrate, an alpha keto acid, which can react with the PLP cofactor anchored to the amine. And ultimately, this amino group is transferred onto the amino acid, replacing this oxygen, which leaves as water or hydroxide, giving us a new amino acid. Okay, so what I'm showing here is a good representation of the chemistry, the type of chemistry that PLP can undergo. Okay, we're going to see many examples of this throughout the semester. This one is a very important one because every single amino acid relies on this reaction to be produced or degraded. Okay, just as a really quick recap. Step number one is the same for every single PLP-mediated reaction. The cofactor starts off anchored to the active site of the enzyme through a shift base with the lysine side chain. The amino acid comes in and replaces it. So we form a new shift base, but now with the amino acid. Step two, in this case, the CH bond is the labile one because it would be in the plane of the pi system of PLP. So it's reactive. And since it's reactive, we can deprotonate that carbon. The electrons get pushed through our pi system all the way down to the electron sink. Step three, the electrons get pushed back up through the electron sink, but this time we're picking up a proton on our cofactor. Okay, so the electrons redistributed. Our cofactor carbon picked up a proton from a general acid. Step four is where we bring in water, specifically in the form of hydroxide. Hydroxide attacks at our alpha carbon, pushing electrons down to this nitrogen, and then simple redistribution of protons will lead to the breaking of the alpha carbon nitrogen bond, forming the alpha keto acid. So our first substrate has come in, the first amino acid. We've produced our first product, the alpha keto acid, and the amine is now anchored to the PLP. That's the first half. The second half reverses everything. We shift protons around. That creates a new bond between the nitrogen on our cofactor and a new alpha keto acid, ultimately leading to the formation of the shift base between the amino acid, the deprotonated amino acid, and our cofactor. We adjust the chemistry, we adjust the resonance of our cofactor to generate an sp2 carbon here instead of an sp3 carbon. We then push electrons up through our cofactor so that we can make our alpha carbon go from sp2 to sp3. So our alpha carbon gets protonated, and now it's in the form that it needs to be for the final amino acid. In the last step, it's the same as every last step. The lysine in the active site comes in. We break the shift base between our amino acid and the cofactor, and we form the original shift base between our lysine side chain and the PLP cofactor. Okay, so not every PLP reaction will be identical to this, but the themes are always there. Step one, swap your amino acid for the lysine. Step two, think about what chemistry has to happen. And then one of those bonds ultimately is going to be labile. One of those bonds you're going to need to break. So it boils down to looking at the products and thinking about how it happens.